Hello everyone. In this video we're going to go through the different rules that we have to know to identify sig figs or significant figures in a number. So often when you're having to report your measurements and maybe you look at an instrument and this, that, and the other, you don't just want to give an infinite amount of numbers. You don't want to say 1.000000000 if your instrument isn't that accurate. And in addition to that, when you're solving chemistry problems, you want to make sure that whatever value or whatever data you're given, when you do calculations, your answer reflects the accuracy of that instrument that allow you to come to that conclusion. So there's a couple rules here we have to make sure that we follow in order for us to solve chemistry problems. So the first rule is that any non-zero digit, all non-zero digits are significant. Essentially, those are digits 1 through 9. Digits that are not 0, we deem those significant. So 14.4 has 3 sig figs. The 1, the 4, and the 4 are all 3 significant. Okay. Rule 2 is known as the sandwich rule. Any zeros that are what we call sandwiched are always going to be significant. So if we look at a number like 5005, this 5 and this 5 are significant under rule 1, right? Because they're numbers between 1 and 9. So these two numbers are significant. However, because these zeros make a nice sandwich between this 5 here and this 5 here, that means these zeros are also significant. So we have 4 sig figs in that digit, or in that value there. The next two rules are where people get confused the most, and that's the difference between a trailing zero and a leading zero. If you're driving a car, and pardon my bad drawing of a car here, let's give it a nice little hood here and something in the back, and then it slopes down, you get some tires, and I'm towing a trailer, right? The trailer is behind it, right? So if the car is going this way, this trailer is behind it. So trailing zeros mean they're at the back end. They're to the right-hand side of the digit. Trailing zeros are only significant if there is a decimal in the number. So let's look at 5,000 here. Do I see a decimal anywhere in this number? No. So because of that, these zeros here are not considered significant. Only the 5 is significant. Now, does that mean I just write 5 as my answer? And does 5 have the same weight, the same meaning as 5,000? No, it does not. And that's because these zeros here are not significant zeros. Rather, we call them placeholder zeros, because I have to have those zeros there to make the number valid. However, that doesn't mean that they are significant in my measurement. It doesn't mean that my instrument could go any further past that. So we would say 5,000 with no decimal has 1 sig fig. Now let's look at the next one. Let's say I have 5,000, but I do add that decimal at the very end. Because these zeros are trailing a non-zero number and there's a decimal, that means each of these digits here are significant. So in this case, I would have 4 sig figs. Now, another thing to keep in mind, let's say I move the decimal somewhere in the middle. Let's say I made it 50.00. How many sig figs are here? Again, it's still going to be 4. The decimal can be anywhere in the number. As long as it's somewhere in the number, the zeros that trail at the back end of it, those are going to be significant. So all 4 of these would be significant. Let's talk about leading zeros. Leading zeros are what come from the front end. So basically the first zeros that you see. In the case of this number here, I have 1, 2, 3, 4 leading zeros. These leading zeros are never significant. Even if there's a decimal here, doesn't matter. Leading zeros don't count. So these 4 zeros, not significant. That means these two values here, the 5 and the 0, are significant. I have 2 sig figs. Why is this 0 significant? Because it's a trailer and there's a decimal. So it's got to be significant. So I have 2 sig figs there. The next one is not one that you would necessarily be assessed on a test or anything like that, or you wouldn't really have to know, but it's important to recognize. And what that's basically saying is if you have an exact quantity, or really a quantity that, let's say, you pull in to a problem, like a conversion factor, those, because they represent something exact, have an infinite amount of sig figs. So for example, let's say I wanted to write a conversion factor that for every 1 dozen apples, that is equal to 12 apples. These do not have 1 and 2 sig figs. These have an infinite amount of sig figs because this represents an exact number. Like exact. I can't have 1.0 dozen apples. You know what I mean? So if I have 1 dozen apples, that equals 12 apples. That to me is an exact number. It's not really a measurement, right? It's something that I know with absolute certainty it's this amount type thing. The last and final rule, and this is another rule that trips people up, is that when you're dealing with scientific notation, we want to identify sig figs based on the number only, not the times 10 to the power of. So what that means is when you look at this example here, we only want to look at the 6, the 5, and the 0. This is all we want to look at. We do not care about this times 10 to the third power. Because what students will often do is this. They'll say 6, 5, 0, 0, 2, 1, 2, 3, yeah. And they'll put a decimal here. And they'll say, well, that's 4 sig figs. Well, I will tell you that is incorrect. Don't do that. Look at the value at face value. How many sig figs does 6.50 have? It has 1, 2, 3 sig figs. So when you're dealing with scientific notation, you only want to look at the value on the front end of it. Now again, all these rules apply for identifying individual numbers and really individual, pieces of data that you are given, usually in a problem. Or maybe it's a final answer type thing. Now, when you do your math, and I'm sure you've seen this with a calculator, if you were to, for example, do a number like 12.0 times 12.0, right? You're going to get something like 144.00 or something along those lines, right? Keep in mind that your calculator, especially if it's not a nice even multiplication or division or something like that, it'll go on and on and on and on, and it might go on for the rest of the calculator screen. Now, does it make sense for something as simple as this to report all these digits? The answer is no. It really doesn't make a lot of sense for me to report all these extra digits, especially if you think about the instrument you're using. Your instrument likely isn't this accurate if these are the measurements you had in the first place. So we want to follow specific rules when we add and subtract. And we multiply and divide. So when you add and subtract, you want to limit the answer to the same number of decimal places, not sig figs. This is a common misconception here with adding and subtracting. You want to limit the answer to the same number of decimal places that appear in the original data with the fewest number of decimal places, not sig figs. So when adding and subtracting, we don't care about sig figs. So in this number here, how many decimal places are there in 100.00? There are 2 decimal places here. How many decimal places are in 50.0? 1. So I have 1 sig fig there. So I take 100.00 minus 50.0. The correct number I should report is the least number of decimal places. So the answer is 50.0, not 50.00. Okay, we don't want 50. This is not good. We don't want this. Too many there. We have 1 sig fig there. We're going to have 1 at the end. So that's another thing. Adding is the same type of thing. If I were to add these two together, it would be 150.0, not 150.00. Now, let's look at multiplying and dividing. It's the same rule as the top one. However, you want to limit your answer to the same number of significant figures that appears in the original data with the fewest number of sig figs. So now we have to whip out those sig fig rules and determine what's the smaller number of sig figs. Whatever that smaller number of sig figs is, That's how I'm going to report my answers. So let's look at the example here. I take 150. How many sig figs are here? 2. 1 and 5. The 0 doesn't have a decimal, so it's not significant. How many sig figs are here in 5.00? 3. 5.00, because that decimal, those trailing zeros are going to count. So 2 versus 3, which is smaller, which is least precise? The 2 is. So I'm going to have my answer be 2 sig figs. So my answer for 150 times 5.00 would be 7.5 times 10 to the second power. If you did it in scientific notation, that's 2 sig figs here. If I wrote it out in normal notation, though, 750. Again, how many sig figs are here? 2. If I were to put ignore that decimal there, 750.00 or 750 with a decimal, both of these would be wrong because this has 5 sig figs and that one has 3 sig figs. One other rule of thumb that we're going to look at as we go through problems is that generally speaking, whenever you end with a value that's, let's say, very large, so let's say, I have many values that I'm plugging in and I'm solving for, you always want to record and round your answer to the lowest number of sig figs based on the data in the question. So again, you might be given this piece of data in the question. You're going to immediately say, well, this only has 2 sig figs, so that's what my final answer is going to be in. Now, keep in mind that you have to also take into account what type of operations you're doing, but as a general rule, it's one that usually will help you check your work at the end of most problems. Thanks for tuning in.